welcome to today's webinar. My name is Adam Golov, Marketing and Communications Manager at Data Conversion Laboratory, and I'll be your moderator today. Before we get started, I wanted to let you know we will allow time at the end of the webinar for questions and answers. So please write your questions in the chat area as they come to mind. If we don't have time to answer them all, we'll make them available on our website. Today, we are thrilled to introduce Mark Gross, President of DCL, and Ari Gross, CEO of SoftWorks AI. Mark is the president of DCL and is a recognized authority on XML implementation and document conversion. Mark also serves as project executive with overall responsibility for resource management and planning. Prior to joining the DCL in 1981, Mark was with the consulting practice of Arthur Young & Company. Mark has a Bachelor in Science and Engineering from Columbia University and an MBA from NYU. He has taught at the NYU Graduate School of Business, the New School, and Pace University. He is a frequent speaker on the topic of automated conversions to XML and SGML. Dr. Ari Gross, PhD, received a Bachelor in Science degree in Mathematics from Johns Hopkins University and a PhD in Computer Science from Columbia University. Dr. Gross has been very active in the research and development of new methods and technology in the area of computer vision, imaging, artificial intelligence, machine learning, and real-time computing for the last 20 years. His achievements include over 40 published papers and several patents in areas relating to imaging, machine learning, and document augmentation. Without further ado, welcome Ari and Mark.
Okay, this is Mark Gross, and I just want to say that I'm thrilled to be doing this webinar today with Ari Gross. It's a real pleasure. He's a tremendous expert in the whole area of computer vision, which a lot of what we're going to talk about is involving. And he's a very busy guy, having just being involved in a new startup that he's working, SoftWorks AI, which I'll tell you a little bit about. So it's terrific we're able to do this. I also should mention we're not related. I don't know if you saw the pictures at the beginning. We look so much alike, but we're not related.
Mark, I'm glad you brought that. I'm glad you brought that up.
I usually have the same question with our CTO at Data Conversion Laboratory, whose name is Michael Gross, not related there either. Anyway, so moving along, you want to put the agenda strike, Adam, the next slide? All right, so today's focus is going to be on image plagiarism, the area of plagiarism has been a major issue in the whole scholarly publishing world, and in the other areas, and particularly in the scholarly publishing world, where it really relates to the professionalism and reliability of scientific research. If you don't, you're assuming that somebody's original research, meanwhile, may have been pulled from someplace else. So there's a lot of stuff being done with textual plagiarism, which I'll talk a little bit about. I think a new area that's really has just come up and not much done with is image plagiarism, where an image has been pulled from someplace else and it's not part of the original research. And that's a bit of a more difficult problem, and that's really what Ari Gross is going to be talking about later on in this webinar. So what we're going to be talking about is just the issues involved in identifying similarity in images. There's the questions of how do you do rapid matching when you start getting to large databases, because when you're checking against, for plagiarism, you want to go against millions of images, so it's not a trivial task. And we're going to talk about a prototype system we developed to test some of the concepts over here to see how well it would work and if it would work. And that's our talk today. I'm first going to talk a little, for those of you who are not familiar with Data Conversion Laboratory, I'll talk just a little bit about that, and then Ari will talk about his company a little bit. DCL, Data Conversion Laboratory, is a woman-owned business. We're in New York. We have 65 employees based in New York and a few spread in other places. Our primary business is converting documents, as the name of the company implies. And I'm not going to read through all of these, but scanning and digitizing is what people think of originally as what we do, but we're really involved in a lot of areas, a lot of conversions to XML and other formats that are used to support big data and all kinds of research. But also involved, a lot of it is not really so much conversion as identifying metadata, identifying information inside of documents, metadata extraction, and as we're getting to larger and larger databases, they were dealing with terabyte databases. You no longer can do things the way you used to 20 years ago of looking at things manually, just checking things out. So the question is, we're very involved in how do you automate these very large conversion processes. What we're talking about today is really in those fourth and fifth bullet items of how do you enrich information, how do you grab information that's not just text, and how do you automate very large processes. And let me just turn this over for a minute, go to the next slide, and let Ari talk a little bit about his new company.
Thank you, Mark. So first of all, it's a pleasure to be here today. We have a very long history of working together with the Data Conversion Labs, and we enjoy the partnership. SoftWorks AI really is a spin-off of a company that's been around for over 15 years called CVision, and CVision really stands for computer vision, because we were a computer vision AI lab, part of City University, and then we became a company at some point, and we really focused on how to make very compact, optimized PDFs. In fact, that's how we first got into image matching, how similar letters look to each other. We're in the United States. We're actually in New York City, a few miles down the road from Data Conversion Labs. We've been a partner of EMC for a long time, but these days it became OpenText. This is really with respect to CVision. Before the spinoff is a little bit newer, but we had over 100 Fortune 500 companies in CVision, which, again, we just sold to a Chinese group. We have IP at CVision where we did a lot of new technology in image matching and perceptual font matching. How close the letters look to each other, when can you match them, fast OCR, super fast OCR. So we have patents in that area. We won the 2012 Red Herring Award for fastest growing companies in the United States. And the spinoff really was focused just on the AI part of our business. But we really, as a company, we're focused on how do you make everything into an optimized image, optimized PDF specifically. And then we got into how do you start taking action on those? How do you recognize differences? How do you auto route? How do you automatically pull off the data and use it downstream for more for additional processes? So basically, we focus in the spinoff on how to use AI to help or augment the knowledge worker in different vertical areas, including finance, tax, and accounting. Yeah. Okay, next slide, please.
All right, so you can see how the two companies really have a connection in going to a very new area. But let me talk about plagiarism. What is plagiarism? It's taking credit for somebody else's work, and it's not just in the scientific. It's an issue with text and tables and figures, music, ideas. All that can be plagiarized. It's become more and more a recurring problem in the STM world, in the scientific publishing world. One is because there's a tremendous amount of pressure to publish in many academic settings, so more and more stuff has to get out there. And the other thing is it's easier to find things when they're plagiarized. There's more exposure on the internet. Even journals that may have had very small distribution in years past are now more findable. So there's a lot more out there that's easier to find. So I think there's two pieces to where the problem has come in. Text is already being checked routinely. There's an organization called Authenticate. There's some others that Authenticate specifically has a very large database of scientific papers against which it can go and do text authentication. There are also free checkers available. So in the text world, there are things out there that are already are doing that. I just want to say that also it doesn't have to be identical in order to be plagiarism, right? Sometimes it's a subjective issue, but if it, it's words might have changed, I mean, it's like you know, in I don't know if you remember if you in school, if you copied something out of an encyclopedia article and changed a few words, hoping the teacher wouldn't catch on, that's still plagiarism. So it's not just an issue of finding something identical. If that was it, it'd probably be easy. It's identifying something that's close, and it's sometimes subjective. And the larger case is how do I identify something that's close from millions of possibilities? Adam, next slide, please. So in text, there are many well-known techniques to do it, which we use many of them. You know, we count how many characters in a paragraph, how many characters or words in a paragraph are matching. There's word wheels, so it doesn't matter whether the words are in exactly the right order. You may want to normalize for synonyms. So if you changed a few words, like in an encyclopedia article, it's still plagiarized. And just in as examples of technology we develop for something completely different, but just example of how you do that is the Harmonizer software that DCL uses, which is intended to identify similarity across large document sets. And the reason we do that is for a positive purpose. A company that has a large collection of manuals, for example, on how to fix jet engines, and many of these manuals will have similar instructions in them. You want to make sure, you really want to find out if things have varied over time. You want to find them so you can get them back to be the same. And also, if you're converting to XML and going into content management systems, you want to be able to find all those identical paragraphs to make them, to use them only in one place and reuse them across many manuals. So that's the reason we developed this tool. And if you go to next slide, please. So and what the Harmonizer tool does, it'll go through a 50,000 or 100,000 page collection and come back and give you metrics on how many of the paragraphs are. In this case over here, the 39% that's in purple on the upper left side, those were exact matches. So and there's numbers over there also. If out of 2,390 paragraphs, 2,015 of them, 84%, were non-unique. 938, 39% were exact matches, and then there were close matches. And there are parameters on what identifies a close match. And again, the reason for finding this is so that you can identify for positive purposes. So the more that is matching, you can pull those out of the set and say those are units that you can reuse. Next slide, please. And besides the chart that we have, what we use in practice is there's a Redline report that shows for each sentence or each paragraph what other variations were found, and it uses a standard technique of redlining, so the things that are not there are crossed out, and things that are there added are in red and underlined. And in this particular case, is identifying in each manual what line in the book is related to that first example. So that's a way that's being used. Next slide, please. All right, so I'm going to turn this over to Ari now. I think the way we deal with it in text, you can sort of conceptually see how it is because you're using word processors and redliners, things like that. Doing it on a large scale, of course, is a different issue, but you conceptually see how that's working. Images adds a whole layer of complexity. And over to you, Ari. Ari, we lost you.
Oh, sorry, Mark, it was on mute. Apologize. So basically, a lot of us are familiar with text similarity, and you might read something and say, I've seen this somewhere before, this quote somewhere before, and it tends to be a little bit of an easier problem with approximate string matching. Why is that? I guess, well, first of all, it's pretty much a 1D matching problem, you go left to right and you look for some similarities, and at least in the images right away we have at least a 2D problem on our hands, right? And then of course if you do things, we're all familiar with sort of the editors you can even do on your mobile phone. You can take, let's say, this picture of Einstein that's in this image, and you could put a swirl effect on it, you know. Well, it's this original image with a swirl effect is going to be a very, very different string. If you look at on the computer, you know, that binary string that saves up the image, once you edit it, is going to look completely different than the original one. So we're stuck with a problem that some of the methods that we're used to where that would work for string matching are not going to work too well when you talk about image approximation and similarity in images. So again, just to, you know, if the images are exact, then that's a pretty well defined problem, right? Identical images is trivial because basically the image at the end of the day becomes a string. Whether it's binary or grayscale or color, it becomes a string. Even if it's JPEG, it's a string. And those strings can be compared, and an exact match is easy to pick up. The real problem, though, is that many of the images, if you're trying to plagiarize someone, you might crop the image, you might Photoshop or photobomb the image. There are things you can do, you know, to take the image and modify it slightly. You can rotate it, you can change the color space. There are things you can do to it where it'll look very similar to you and me, and we'll actually say, well, maybe this was taken from somewhere else. But the images, the strings that you're comparing are going to look very, very different from each other. So it is a more complicated problem, and something, though, nonetheless, and we as a company are trying to find ways for machines to play using AI and other technologies to figure out things that humans can actually figure out. So typically, if someone wants to look at all these by hand, they will say, you know, oh, this image looks like this other image, and we need computers to be able to see the same things at the end of the day. So this is really about a pilot that we're working on in conjunction with DCL to have a computer automatically determine whether two images are in fact similar under some transformations. Next slide, please. Right, so a reasonable question that you could have is, hey, wait, isn't this technology already out there? So for example, I can go to Facebook and it will identify in a picture my family members and my friends, and it will label them. How does that happen? If this technology is already solved and already commoditized, then, you know, why are we saying it's a challenging problem? So really we want to limit, you know, the problem scope. In other words, if you knew that the problem was narrower, let's say it was just face recognition, then it would become much easier to solve. So if we're looking at face similarity, one of the things we're going to do in a picture is look for faces. We build a facial detector. It's looking for sort of an elongated elliptical construct in grayscale color space. And you can see that when you take a picture, sometimes it's finding the faces, sometimes not, depending when they're in focus. But if you know that you're dealing in face space, then that's already a restriction on the entire image universe, which is a much larger universe. So once you limit that universe to faces, you can do things. You can, you know, find the face, and then once you have the face, through different methods, you're going to try to find the eyes, which should be symmetric, build a symmetry axis, look for the nose, find the ears. So once you're able to solve for the face in an image or any series of faces in an image, you can then compare it against faces of friends of yours. So at least two advantages that you have if you're dealing in Google or Facebook and looking for friends is, number one, you're looking for faces, which is a much narrower problem than comparing all images to all other images, right? And in addition, you typically know who your friends and your friends of friends are, so you would have some sort of graph structure telling you don't need to look at 7 billion images of everybody on the planet. You only need to look at your 50 closest friends and relatives, for example. So it can be solved in certain constrained domains, but that doesn't help the harder problem of how do we determine for two arbitrary images how similar they are to each other and whether in fact they're plagiarized. Next slide, please. So just to give you an example, what you really want to do is recognize that an image started really from another image and was transformed somehow, right? What we'd love in a perfect image plagiarism detector, and again, it's part art, part science, because you may show two images to each other, and maybe someone will tell you that the second one was plagiarized from the first, and maybe someone else won't see it. So it really depends how similar they are. So it's really a measure in a continuum that you're talking about. But if they're similar, you want to detect they're similar. Normally, we would say they're similar because you started with one and you transformed it into the other. So for example, we look at image transforms. They include rescaling. That's the one in the upper left. You've taken that truck that, you know, just had an explosion occur, ran into something, and you take another version of that that's on the right. It's larger. That's rescale. Occlusion, that's the upper middle picture. It's the same original picture. The right is the left, but now you've occluded it. Maybe it's a text box. Maybe it's some other information. You could put a whole bunch of things in front of that truck. You could photobomb the truck. So we are concerned about people taking an original image, and maybe now you're showing that so-and-so, Marilyn Monroe, was in fact in front of this Eiffel Tower, and you're putting these two images together later, and it might be helpful to understand that that background was really lifted from somewhere. So that would be detection under occlusion. Color remapping, you may want to remap the color space. So in this case, it's the same image, but we've changed the color channels. But you'd still want to know, at least I would if I was a publisher, that the right image was in fact very, very similar modulo the color remapping to the picture on the left. Then you look on the lower left, that image cropping translation, you may go and crop the image, take a part of it from the original, don't take all of it, or you may want to translate it. So these are all kinds of image transformations that people do. We all do some of these. I do these on my mobile phone. When I go on vacation, I'm cropping and scaling and doing all kinds of things. But really, they all came from the original picture. And you sort of want to be able to find that out programmatically, automatically, if possible. The one on the lower right is rotation. Again, it's the original image rotated. So in a perfect system, image plagiarism system for, you know, that you'd use for publishing or for patents or homeland security or anywhere where you want to understand image similarity, you'd want to pick up all these transformations in an automated way. Next slide, please. Let's talk about hash functions briefly. So a hash function is a mathematical function that can transform a arbitrary size, a large size packet of data into a fixed size output. We use that quite a bit. One hash function you might be familiar with is called the Loon algorithm. It's a hashing function over a 10 modulus that gives you a checksum signature to see whether a credit card number is in fact valid or not. And that way you'd know if it got warped, if you're sending it over mobile and one of the letters, the digits got permuted, the checksum wouldn't add up and you'd know it wasn't valid. So that's just a simple example of a hash function. Checksums in general are use hash functions. So we're going to talk about a few different kinds of hashing. Cryptographic hashes can be used to verify authenticity. So for example, we use them in the Adobe PDF standard. If you can hash your PDF such that you know that no one has modified it after you touched it, that was the final version of that. And that's very useful to say, again, we signed this document, no one has touched it since then. You would use a hash function such that if anybody changed it, the hash would no longer add up. Perceptual hashes are a little different. With cryptographic hashes, if you change things at all, you don't want to get the same hash function. And it doesn't matter if you're in that neighborhood, because the whole notion is you want to be sure that no one else has been in here and tampered with the data. Perceptual hashes are a little different. You want to map a very large space to a much smaller space. But what you do want is a correlation, meaning you want a meaningful comparison between hashes such that similar images are going to be very similarly located in the hashing space. Okay, and the idea is that if the image was plagiarized, you could find it because the hashing values would be very similar. Next slide, please. So let's talk about perceptual hash functions. We're going to really focus on that right now with respect to image similarity and dissimilarity. So one method, for example, is averaging. And in this case, we're first in this case, what we did, particularly for this example that we try to build a POC with respect to IEEE, is we first normalized all the images and mapped them into an 8x8 space. So everybody was normalized in the same image space. So that was normalized. And so then what you then do is you take the average pixel value for the neighborhood, and we'll see how you get a signature from that you can use to compare. Differencing is very similar, except you sort of look at a neighbor. It's more of a local compare, and it's going to be invariant to things that averaging would not be, like occlusion. And then DCT is nice because JPEGs are already in DCT format. So sometimes you want to come up with image comparisons that take advantage of the native compression format. So it's very nice about a DCT hash function. You already have a JPEG. It's already in DCT format. You don't need to unwind it. You can use it directly in that format to determine similar images. So these are three hash functions we considered when we were looking at the image plagiarism prototype. Next slide, please. Just give an example of how averaging hash functions work. So in this case, we start with this truck example that we're familiar with, and then we first rescale it. So we're showing you how we normalize it, and part of what we do here in Perceptual hash space is we try to normalize the images so that we're dealing with initially the same dimensionality. So here we take this image, whatever dimensions it might be, rescale to an 8x8, initially keeping the color. Those are color averages. Then mapping the color to a grayscale image, still normalized in an 8x8. And then we get a binary signature, which of course maps to a binary string, which we're going to use to compare image similarity. So in this case, again, if a pixel was lighter than average, we made it white. If it was darker than average, we made it black. So every white pixel becomes a 0, every black pixel becomes a 1, and then you basically take this image here, and no matter what its dimensions are, and the fact that it's in the color space, you get that string shown on the bottom, which is its average hashing function. And theoretically, another image close to that would have a very similar hash function. Next slide, please. Right, in this case, we're looking at a difference hash function, and we're doing something very similar, except instead of taking the average, in this case, we're taking the difference. And that means, of course, it's a local measure. You might say, well, how is that really different? So again, it's the 8x8 that you're mapping to. So you first normalize the dimensionality of it. Then you normalize for the color space. Because again, we want to say they're similar even if you remap the color space. So we're normalizing for color space. We want to say they're the same even if you rescale it. So we rescale it to a canonical 8x8 and we take the color out of it, right? So that helps us normalize, gets it invariant to these different transformations. But what happens if you occluded it? If you put something else in here, if you photoshopped it, you put something in front of it, a text box, another figure. So the average is going to change, and if you use the average function from before, then this hash function will not be invariant to things like photoshopping it later, adding something in the front of it to occlusion. So we want to try to make it invariant to other things, and that's what we're going to show you. We actually use the blended measure of 3 hash functions that include this function, the averaging hash function, because sometimes one hash function will see one attribute and it won't see another. So the averaging hashing function is useful, but in occlusion cases, it's going to fail. So we want something invariant to that, so we also use a different hash function. In this case, you're comparing it to local neighbors. In particular, you fix a local neighbor, could be your leftmost, which supports a raster scan traversal of the string. And if it's darker, we map it to black, which is 1, otherwise we make it a 0. So again, it's a hash function. You get a binary string, and what we're hoping is that another image similar to it is going to give us a very similar binary string. Next slide, please. Okay, so we can also talk about DCT hash functions, and for those, a lot of times you do need to worry about speed because you might have a database with 1 million or 1 billion. In the case of Homeland Security, you could have hundreds of millions. The databases could get very large very quickly. So you really do care about speed. And a lot of times, these native images are going to be kept in DCT to begin with because DCT, discrete cosine transform, is how JPEGs are handled. So it's very nice you can come up with a perceptual hash function that works in JPEG space, which this one does. So we use 3 hashing functions. One is the average hash function, one is the difference hash function, and this one, of course, is DCT based. The various perceptual hash functions each convert the image to a different string. They're not looking at the exact same attributes, similar attributes, but not identical. Each has its strengths and weaknesses. So you want to use several of them to get optimal results, and we weight them. We get a weighted value that combines these three similarity metrics together. As long as the same protocol is used on both sets of images, you can actually get a meaningful comparison. Next slide, please. So just to talk about the POC, in this case, we have a database of 10,000 images, 1,400 technical papers by IEEE, but a user interface that lets you load images from a paper, and it would automatically check similarity to anything in the database. This pilot had 10,000 images in the database, but you can see the speeds we're talking about here. Nothing to preclude it from working on 1 million, 100 million, 10 billion images. And what we did was for every document, image, for every paper that you needed to worry about plagiarism for, we take the images in that paper and compare each image to everything in the database. And what the system does is it comes back with the closest matches and the scores, the weighted score for how close they are. And then we let the user decide whether they're close enough to, in fact, warrant a concern about plagiarism. So there is typically a human in the loop here, although you could put a cutoff and say, if it's further than 20 away or 30 away, don't even show it to me. But the bottom line is, if you're looking at a paper and it has 8 images in it, and you've got 20 million images in your database, it's going to tell you in just a few seconds the closest images known in the database that you might have to be concerned about with respect to plagiarism. Let's talk a little bit about scoring. So we used all 3 hash functions, averaging, differencing, and DCT. We combine all 3 together. For each one, we counted the number of different bits. That's called a Hamming distance. What is the bit difference between the 2 binary numbers? A lower number would indicate more similarity. If they're exactly the same for that hash function, we expect a score of 0, right? And we added a weighting. We put together some weighted score that we thought matched, to some extent, your perceptual recognition for image dissimilarity. And that's how we got the scoring function to work. With respect to speed, give you some idea of how fast the thing ran. On average, it took about 1/4 of a second to generate the 64-bit integers, because for each hash function, we had a 64-bit integer. It took about 1/4 of a second to generate the hash functions, the 3 perceptual hashes we used. And with respect to image comparison, we're able to compare images to the stored values in the database at a rate of 8 million images per second. Okay, so what we're saying is that if you had a single image from a journal and you wanted to match it, it would take you about a second, that's per core, by the way, to match it against 8 million images and determine how similar or dissimilar it was. Next slide, please. So just give an example here, pilot output, so you can see what's going on. In this case, we're looking at the uploaded image, that's the upper left. And then we had in this paper, so again, we didn't plagiarize for this experiment. So these are actual pictures that were other journals, pictures from other journals that were in the database. Right? So we see here collection match number 1. So it's rating the system and saying, look, if you're worried about plagiarism, this one scores a 0. Well, this happens to be the identical image, and it should score a 0. And then it's also saying, well, of the 10,000 that we used in the database in the POC, you know, the second closest match is this one on the right, which is not an exact match, but it's close, and I got a score of 2 as opposed to 0. And then it shows you the third closest and the fourth closest. So basically, the system can order in a perceptual metric space the images closest to this initial target image and those that are further away and further away, and you can have a human look at the closest ones and determine whether plagiarism is a concern or not. So again, the method, the first image is uploaded into the system can identify the K most likely matches. In this case, K was set to 4, and you had the 4 nearest neighbors. Okay, yeah, next slide, please. So we also see with respect to close, nearly identical images, this is the second image, the second closest one, and it looks like it is similar, but it also looks like it's not exactly the same. It appears to be wider. The color spectrum on the top seems to be similar. So perceptually, you know, we would see these as similar images, but not identical, and the system also saw them as similar, non-identical images. Looking on the image below, we see two files, and these do look somewhat similar. Again, not at all identical. So there's two images here, basically. There's one on the left that has 4 quadrants and one on the right with 4 quadrants. And we see that they're similar, but probably, there's no plagiarism here, but we might want to show it to somebody. So this got a further score, meaning you see that some of these graphs are quite distinct from each other. So while the one on top scored a 2, because perceptually they're very close, the one on the bottom scored a 12, because there is some similarity, but not nearly as much similarity. All right, next slide, please. Right, and here we take a look at two things. This is sort of interesting because sometimes you might get the same score, but you're dissimilar for different reasons. So in the first case here, the color schemes were very similar, but we added some stuff. So right, so in this case here, the color schemes are similar, but you can see we have an orange box under the truck on the right, and the explosion has been permuted on the right, so it's not the same explosion. So the contrast changed, but the image similarity is there, and it has a score of 20, which means, it looks similar, but not exactly the same, right? And in fact, maybe you want to show it to a human because the one on the right does look different from the one on the left, but it doesn't mean that we haven't used components of the image on the left to put together to generate the image on the right. So it still might be something that someone needs to look at. And we also see a score below, which is sort of interesting. Here the shapes are quite different, but what we also have in the 3 metrics we used is the ability, if the color schemes are exactly the same and the frequencies of each color are the same, you're going to get a pretty similar score, even though the shape has been modified. Okay, so again, the system, what it's meant to do and what it does do is it can take a very large database. We used, I think, 20,000 in the pilot, but you could have 20 million or 20 billion images and know in a matter of seconds or minutes what the most similar images are in that database. And then you can, typically with a human at that point, determine whether plagiarism is a concern or not a concern. And so with that, next slide, please. Mark, I think I hand it back to you at this point.
Yeah. Okay, that is great, Ari. So I just, other uses, I mean, we're really looking at one particular case over here, and I'm just in terms of technology is of interest, I think, and suitable in a number of other places. Just some examples over here: authentication of signatures and documents, which I already touched on a little before. Detection of watermarks is an area where this might be of interest. Not just, this isn't, well, we're talking about images, but similar approaches and similar algorithms will work with songs and advertisements and stuff like that are played on the radio and television. So this technology can be used for those kind of things. Keep track of every time a particular ad has been played someplace in the world. Another area that finding trademark usage. I mean, identifying trademarks is a major issue around the world. So this technology might be used over there. And actually, we talked about signature verification in the first bullet. I was just so excited about signature verification. So I think so. There's a lot of other places where we're looking at things that we're trying to identify similarity that's not words. And that's really, I think, the point I was trying to make over here. Next slide, Adam. So where are we going? Where are we going from here? So as I said, this is a pilot system, but I think what we've proved is that first of all, you can use this to identify similarity of images. I think there's, as I mentioned at the beginning, and Ari pointed out, we're really using a few different algorithms over here. There are many others that we've thought of, or as Ari's thought of, and we've not really examined over here in this context. But in a live system, there's some fine tuning you really want to do, depending on what it is that you're looking for. Like that last set of images we looked at that identified two as sort of similar because of just the color space being there. Maybe you downplay that and play out some of the other parameters, but there's a lot of adjustments that can be made over here. So I think building the system out, we would there's that kind of analysis that needs to be done, layering additional algorithms and fine-tuning how you weight them so that you really get closer. In any kind of large matching situation like this, you want to be able to identify all the possibilities, but then take out all the ones that are not possibilities, so you don't have to look at a lot of stuff. You don't need humans to look at a lot of stuff. You want to be only able to look at, it's like when you look something up on Google, you don't want 3,000 possibilities. You want the top 10. So those are two things that are going to be needed to be. And then we have to there's an infrastructure that needs to be built to build this to really deal with multi-million image processing, and it's really. This infrastructure we've already built for other uses, so it's not very difficult. The big time-consuming piece of it is taking your database out and building the signatures, going through the algorithm for each of those, which could take, we said a quarter of a second, I think, for each image. If it's a billion images, that'll take a while. That could be done in background. That doesn't have to be done on the fly as you're doing an analysis. You can do that you can seed your entire database up front to make sure that it has that, and only on the fly you just do the additional ones, or just the 10 images that you want to examine. So you need to have this large database and preset it, and then even the user interface we already built can do that kind of examination. And I think, just in terms going back to what your algorithms are going to be, some machine learning techniques that probably can be used to improve matching on large data sets as you go into different kind of approaches. Next slide. So we're ready for questions. I just before we do that, I just wanted to make mention of it. So the other piece that really needs to be done is to identify if you're going to actually build an image plagiarism system. You need that database of images like Authenticate has for text. So that would be one of the next things that needs to be built. There are organizations that have these large sets of images, like IEEE that we spoke to about already, where we got this test set, but you probably need to build a larger amalgamation. So the first step is really, in terms of building a practical system, is to find that data set and build against it. But I think the same issue comes up with any large data sets. I thought this was a very interesting approach that I thought would be interesting to many of our listeners. And with that, I'll turn it over back to Adam with any questions.
Great, thank you, Mark and Ari. A very informative webinar indeed. We have several questions that have been submitted. The first one being, can you detect image plagiarism when a color image is remapped to grayscale?
Yeah, thanks, Adam. So in fact, we can, and in fact, one of the things I think we were showing earlier is that we need the plagiarism to be effective. We need it to really work across color mapping, because one of the simplest ways to plagiarize someone else is just to remap the color space, and it's pretty trivial to do in Photoshop, and you want to be able to pick that up, and you could remap it by just mapping it to grayscale, and you want to be able to pick that up as well. So I think we saw just from the steps here, just in the normalization, that we map it to the 8x8 and then we map it to a grayscale. So in point of fact, we're going to be invariant to all color remappings of an image, including mapping it from color into grayscale.
Great, thank you, Ari. The next question that's come in is, it sounds like a great idea. What's holding it up?
I think I'll take that. I think there's two pieces. I mean, one is, well, there's probably more two pieces, but the biggest one is identifying these large data sets that can be used. You really want to be able to go against the universe of images. So it's probably going to be, I don't think any one organization has a big enough image set. I think it would be something we'd want to work across multiple image sets. So it's probably, so we haven't started approaching that, but that would be, I think, to put these image plagiarism in real life would be a big piece would be to identify that set. And the other thing is, and this is we need to do some testing on it, but clearly, if a journal wants to do this, and they would also, and there is, while we would automate it to try to get it to a smaller possible set of images to look at, people would need to ultimately make those decisions as they do for text plagiarism. So there's two pieces that need to be built up in order to do this for this particular use case.
Great, thank you, Mark. The next question has come in is, was the IEEE pilot integrated into the manuscript submission and peer review software?
Right. So it wasn't. I mean, it's not. This really at this point is a pilot to examine the feasibility of doing image matching. If it were to go to the next step, I think it would be part of the whole system, as it would be for any publisher or journal or anybody who's using it. You'd want to put it into the workflow. But the way it works is really it's a module that can be put into any workflow. So you'd probably in real life you'd want to do everything you're doing would probably be done as in a specific workflow to minimize the amount of work that's needed.
Great, thank you, Mark. The next question has come in is, are there limits to the type of images that can be analyzed?
Should I take that, Mark, or do you want to?
Ari, that one's for you.
Okay, thank you, appreciate it. So I mean, this is a very interesting question, and to me not trivial. So, for example, the problem of what constitutes plagiarism for Homeland Security is distinct from what would concern the United States Patent Office, is different from what would be concerned to IEEE. So even though we believe that image plagiarism is pretty well defined, I mean, if things look very similar to each other, you'll recognize it, but there are areas where there's specialties. If you look at how you might match in a patent filing models that are under rotation. These are complicated, and I think they're solvable. But again, I think there's a lot of image plagiarism that is, I would call it low-hanging fruit, where basically images are clearly, taken from each other, and that should be detectable. So I guess the short answer, or maybe we've already made it a long answer, is we don't really see limitation, meaning whatever humans can do in detecting similarity, dissimilarity, we believe machines can do when tweaked appropriately. There may be areas of specialty, patents, it would be one area, but there are many other areas where the system needs to be a little bit trained or become an expert in the art to understand what's plagiarism. So sometimes it's more trivial, but sometimes a little bit less trivial, but we believe nonetheless can be automated.
Right. I would add to that just. I would have just said no. There's no limits, but I would add to what Ari just said that there's many complicated areas where you're not just trying to match the image, but you're trying to do other things like understand the image. And I think this is where technology is going now. I mean, we're artificial intelligence, and this computer vision we're talking about today, really, but artificial intelligence and machine learning and all those pieces go together as you're trying to mechanize this. As you're moving along with various technologies we see just over the horizon, I think all these are going to come into play.
Right, Mark, if I could just add to that, I think that's a very good point, meaning knowing how similar images are is one thing, but really understanding what's in them is harder still. And then if you want a machine to be so sure it knows what's in them that it's willing to take action without human intervention, that you need to really be sure that's a higher level still.
Excellent. Thank you both, Ari and Mark. The next question that's come in is, have you considered a multi-publisher initiative like Cross-Reps similarity check?
All right. So yes, we have, and I think we're in the beginning stages of identifying organizations like that to approach. So this is an initial step, but that's clearly the way to go. A multi-publisher association. Yeah, I mean, part of the reason we're talking about it here and have at various conferences is to generate that kind of interest. So yes, I think it has to be something like that.
Great, thank you, Mark. The next question that has come in is rather long, so please bear with me. Have you analyzed how well this works for Western blot bands? I would imagine the black versus white content is similar between many distinct images.
So I'm not sure I fully, if I could just trouble you again to just repeat that question, I'm not sure I got all the nuances there.
Sure, Ari. Have you analyzed how well this works for Western blot bands? I would imagine the black versus white content is similar between many distinct images.
Right, so Adam, after Western, I didn't get all the three words there. How Western?
Sure, it's Western blot, B is in boy, L is in Larry, O is in Oscar, T is in Tory.
What?
A band.
Interesting. So we haven't, and again, this is where machine learning can play a role, because what's going to happen here is you're going to come up with a general metric, and it may say that these two images are in fact pretty similar. And we see this all the time in taxonomy space, but yet humans who understand that area are saying, well, these are actually, they may look the same to you, but they look very different to us. And that's where machine learning can actually start learning very, minute differences that maybe the general similarity metric didn't pick up on. But over time, since someone's feeding it that these are different, machine learning will pick up on it, and it will actually increase the perceptual distance and learn that they're in fact distinct.
Great, thank you, Ari. The next question has come in, there's several more. The next question has come in is, do images within a manuscript need to be extracted before they can be effectively compared against a database of images?
Mark, do you want to take that one? Or?
Yeah, yes. I mean, I think you do have to separate out the images and keep it as a separate item, because otherwise you've got all kinds of other things going out. But that's also, depending on what the source document looks like, that can be an automated process. I mean, actually one of the early projects one of the initial projects I worked on with Ari is a process to remove the images, and we talk about patent documents to identify all the images and pull them out and build a separate set of images. So it does have to be separated, but that can be automated also.
Excellent, thank you, Mark. The next question has come in is, in the absence of a centralized database, do users only compare to their own database of images?
Right. So, yeah, you can only compare to what you have. So, you have to you're either building against your own set of databases, your own images, or there may be publicly available images, but you have to build. I think the way this is structured, I don't see another way of doing this, to build to have a database of images that you can work against. Now, you don't need the actual images themselves, because once you've picked up an image, you can build a signature, and that's what you need on your database. So, I conceive of publicly available database. You could just pull an image and do it and build a signature against it. But you do need to have the images someplace to be able to compare against. Have I got that right? I mean, I'm picturing it.
Yeah, I mean, I think that's basically correct. Obviously, you could have your own search tool or some other web aggregator aggregate all the known images it can find that are unrestricted on the web and stick them in a database. But The problem with that is that you're now pulling from all kinds of domains, and a lot of it might be garbage, and then you may still, the images you really care about might be in restricted areas you can't get to. So I think you get the most meaningful results. I'm not precluding running it against some universal database if that's available, but I think for the most part you can get meaningful results if that database or domain is restricted to the most relevant images you're really worried about plagiarism from.
Great. Thank you, gentlemen. We have a couple more questions. The next one's also a rather long one, so please bear with me. What are the effects of cutting and pasting from application to application when dealing with raster images, including reimplying JPEG algorithm?
That one's yours, Ari.
Thank you. Okay, I'm happy to be there. So basically, you know, it's a nice question. We expect to be able to pick these up. Again, you know, one of the nice things, okay, so look, what we showed you here today was a rather streamlined plagiarism system that was a POC for IEEE. But of course, variations of that would be able to consider local hashing functions where you don't only do a hash on the whole image, you might divide the image into a grid and take many, many hashing functions, because by, you know, the coincidence of a 64 by 64 in an image matching another one is highly unlikely, coincidentally. So the methods we showed here are pretty general, but what you can do, in fact, is add additional hashing methods to handle a lot of variations. If you talk about cut and paste, of course, it's a composite of a whole bunch of images. You should be able to pick that up. Again, what we recommend there might have an additional hashing function, which would be a very local aggregation hashing function that would never look at the whole image, but would take little snippets of it and then take all those together, such that if any snippet or a series of snippets matched another in the other image, it would already say, look, these look very surprisingly the same. And I think what's interesting there is it doesn't take a huge number of matches to tell you that you're probably looking at a similar image, right? I mean, if a section of that image matched exactly, that would be a concern. So cut and paste is interesting. I think in this, the one we set up here for IEEE, it may have a little bit of a hard time because it's assuming that essentially there was one image that was plagiarized, but you can definitely modify or tweak the method we showed to handle a lot more variations, including the cut and paste example that you just asked about.
Great. Thank you, Ari. The next question that's come in is, can your software check images for splicing or more complicated image manipulation rather than what are considered to be more visually obvious manipulations, or what you are labeling as perceptual differences such as color, shape, cropping, and resizing?
Right. So I mean, the simple answer for that is yes, it can detect. It can detect all those, even if visually you don't see the similarity. It can pick them up. If you talk about splicing, again, what we can do easily is put in one or more local hashing functions that say, look, if a local signature, if you think about, you know, if you pick a random 128 code and someone else picks a 128 binary string, what is the likelihood those two are going to match? Well, we know it's 1 over 2 to the 128. It's very unlikely that even 128 pixels will match. The normal image, if you think about an 8.5 by 11, is sitting at about 10 million pixels. And the likelihood that a consecutive string of 128 will match is in the trillions of trillions that it would happen coincidentally, right? So there's a lot of very local hashing functions that you can use to amend or to enhance this method that would be invariant to really mixing that image up, like splicing, like swirling, creating a swirl effect. There are invariant methods that will work across those transformations.
Great. Thank you, Ari. The last question that's come in is, how does your software access a specific database?
Mark, you want to do that one?
You got to, Adam, can you repeat that question? I didn't quite get that.
How does your software access a specific database?
Okay, so I mean the software right now is I mean, it could be right now. It's really working with one database in the pilot stage, but it's written as a module that can pull any kind of data. So it can be adapted to any image database, any collection of images. So right now it's really working as a file structure. That's all it's doing, but it can be adapted. It's really the critical element of here is how it's doing the matching, which is what we did that I think was new and novel, but it can be attached to any database, really.
Great. Thank you, Mark, and thank you, Ari, and thank everyone for attending today's webinar. This will conclude today's broadcast. You will be able to access the recorded version of today's webinar in the webinar archive section of our website. Also, our next webinar will be next Thursday, October 26th at 1 p.m. Eastern Time, titled New FDA Drug Listing Rules, Understanding the New FDA Rules for Updating Drug Listings in Annual No Change Certification, being presented by Howard Schatz, SPL Project Manager at DCL. Thank you, everyone, and have a great day.